Hello, this is Frank Owen, PolyX Engineering Incorporated, San Luis Obispo, California. This is a video in our accident reconstruction series that deals with calculations involved in a vehicle at speed braking to a stop. What we're going to do is we're going to apply the principle, the dynamics principle of work energy. In a collision, often braking precedes a collision as the drivers try to avoid it. We'll look at a simple case to start out with. A vehicle will be traveling at a certain speed. Brakes will apply, full braking will apply, and the vehicle skids to a stop. We'll apply the work energy principle of dynamics to determine the length of the skid, both the physical length of the skid, but also the duration of the skid, the amount of time that it takes for the vehicle to slide to a stop. We will do an example later, and we'll have a car traveling at 60 miles per hour. Full braking will be applied. The vehicle skids. The tires skid on the pavement. That exerts a friction force which takes energy out of the system. Initially, excuse me, the pre-braking energy was all kinetic. It was all associated with the velocity. And the kinetic energy from basic dynamics is 1/2 times the mass times the initial velocity, or the velocity squared. As this energy is extracted from the system by braking, the velocity diminishes. It becomes less and less. Tires lock and skid along the pavement. And the skidding continues until the automobile comes to a complete stop. At the end of the skid, the velocity is 0, so there's no longer any kinetic energy in the system, or any energy in the system. And all the initial energy has been extracted by the action of the frictional force of braking. One thing that's important to be cognizant of here is that the frictional force is constant. It does not depend upon the velocity of the vehicle. So it does not change during the skid. Here's an expression for the frictional force. The frictional force is equal to F, which is the drag factor. It's the way it's named in accident reconstruction, but it's more in engineering, it's known as coefficient of friction. The mass of the vehicle, and then G is the acceleration due to gravity. In the English system, that is 32.2 feet per second squared. We will apply the work energy principle, and basically what we're saying is that the initial kinetic energy is equal to the energy extracted during the skid by the frictional force. That's written in words there above, but then the expression is written in equation form below that. On the left is the kinetic energy, the initial kinetic energy, and on the right is the energy extracted during the skid. In accident reconstruction calculations that I make, I like to use the subscripts I and F. I stands for initial and F stands for final. I find this is more useful than using, for instance, 1 and 2. Often in a collision there are two vehicles involved, and it leads to confusion to use 1 and 2, in my opinion, almost anywhere, because does 1 mean initial, or does it mean vehicle 1? So I like to use I and F for initial and final states in accident reconstruction calculations. Since the frictional force is constant, the work that is performed during the skid is simply that frictional force times the distance through which it acts. An interesting point here, if you look at this equation, the left-hand term and then the right-hand term, is that actually both of them have the mass of the vehicle in them. And what that means is that you can actually cancel those out, and you wind up with the simplified equation below without the mass of the vehicle in it. Now this may seem odd. One would think that a heavier vehicle would take more force to stop it, and that is indeed the case. But notice that the braking force, as appeared on the previous slide, is the drag factor times the mass times G, the acceleration due to gravity, and therefore mg is the weight of the vehicle. And what this means is that a heavier vehicle is going to have a heavier braking force. So we will do an example here. We'll have a vehicle traveling at 60 miles per hour. When the brakes are applied, fully engaged, we'll use a drag factor that is typical for dry pavement, 0.7. And what we're interested in knowing is how much time does it take for the vehicle to come to a complete stop, and then how much distance is traversed during the skid. We start off with the equation we worked out before, the energy balance. Initial kinetic energy is equal to the energy extracted in the skid. And I've performed this in numerical format too, or expanded it in a numerical format. And I'm going to go into a little bit of detail on how you deal with the units here, because in my opinion, the unit calculation is an integral part of actually really any engineering calculation. And if you don't do the unit calculation correctly, you can get into big trouble, especially in the English system. So what we do is I have a system that I use for canceling units, like units. Notice, for instance, with the mile cancellation here, I use a single strike that runs from lower left to upper right. For the hours, I use a single strike, but that's opposite. That runs from upper left to lower right. And then for the seconds, I use double strikes. The reason I do this is that you can go back and check your unit calculation later. Your unit calculation will often tell you whether your numerical calculation is correct or not. So I can't emphasize too strongly that you need to have a system for doing these unit calculations. Notice that it's a little bit complicated here because we have terms that are squared, unit carrying terms that are squared, so you have to be careful about that. There's actually feet left in this equation too. There's 1 foot in the denominator, 32.2 feet, but then in the upper, in the numerator on the right, we have 5,280 feet, but that's squared. So we have feet squared in the numerator, in the denominator, excuse me, and feet in the denominator. Let me say that again. We have feet squared in the numerator and only feet in the denominator, and so those will actually cancel out, and you will wind up with feet as a result. That's shown in this calculation here. We are calculating a distance, xf, and we have the result in feet, which tells us that we are that our unit calculation anyway is correct. When this calculation is performed, we find out that the skidding distance is 172 feet. I'll show this in some detail, how you do this in Excel later on in this video. Now, we have the distance that we skid, but we don't know how long it takes for this to occur. This is something that comes up in dynamic calculations all the time, dynamics calculations all the time. You can solve for distance, you can solve for time, you can solve for velocity, acceleration, etc., etc. And there's a certain set of formulas that you use, principles that you apply that are limited, but you use them over and over and over again. So what we want to do is calculate the time of the skid, and for that I'm going to use a standard formula that relates the change in velocity to acceleration and time. This actually comes from the definition of acceleration. Our final velocity is 0. We skid to a stop, so that's 0. And with that simplification, we can solve for time. Time is equal to the initial velocity, the negative of that, divided by the acceleration. But for this solution, we need the acceleration. We don't have the acceleration. We do know that A is a constant because the braking force is constant. To get A, we employ a different formula that relates velocity, acceleration, and distance. notice that the time does not appear in this formula. This is another one of the standard 1D dynamics formula that basically fall out of the case of constant acceleration and the relationship between distance, velocity, and acceleration. So we're going to take this equation and integrate it. If we do that, I like to use definite integrals because, well, I don't know, I guess I'm just used to that, but in my opinion, it keeps your thinking straight. One thing that's true here is that since our acceleration is constant, we can pull it outside of the distance, the displacement integral, and it just becomes a constant multiplier. If we integrate, we get this result. Our final velocity is 0, and then we can start measuring our distance from wherever we want, and just for convenience sake, we will let x equals 0 be the point at which we start our full braking. And this leaves us with this formula here for acceleration. One thing that's interesting about this is it shows we know that our velocity is positive. Actually, even if it were a negative, we're squaring it, so that's going to be a positive quantity on top with a negative sign in front of it. And then we will measure the distance to the right, so xf will be positive. So what this shows is that the acceleration is negative, and it should be because the car is slowing down. It's decelerating. The speed is diminishing. Now we'll set up these numerical calculations, which I'll perform later on in Excel. Let's do a unit check here. One thing that happens in doing these type of calculations in the English system is we humans like to think in miles per hour because that's what we're used to and we have an intuitive feel for it rather than feet per second. So we're constantly converting usually from miles per hour to feet per second, but maybe vice versa too. And therefore, we use this 1.467 conversion factor. There's 1.467 feet per second per mile per hour. So we will often convert our miles per hour into feet per second. We use the acceleration formula that we worked out before. And if we do that, we substitute our quantities in, our unit-bearing quantities in. We will have feet squared per second squared on top because we square that quantity and there's feet on the bottom. So the overall result of this will be feet per second squared, which is a normal acceleration unit in the English system. We're also then going to calculate our time after we get our acceleration. And we worked this out before. Our time is equal to the initial velocity, the negative of it, divided by this acceleration. The velocity is in feet per second. The acceleration is in feet per second squared. And what that will lead to then, if you do the unit calculation, is t will be in seconds, which is what we would expect it to be in. This is a simulation of the car skidding to a stop. It starts off at 60 miles an hour at t equals 0 and decelerates at a constant rate which lasts 3.9 seconds. The total duration of the skid is 3.9 seconds, almost 4 seconds. But note that the car actually reaches its halfway point about 86 feet in less than half the time. And that's simply because the car is going faster at the beginning of the skid than it is at the end of the skid. I recommend using Excel for these accident reconstruction calculations and do it in somewhat of an orderly fashion that is being illustrated here. So we'll start off with an empty spreadsheet, and in the first cell here we will type in skid to stop calculations. Okay, and let's make that bold. Control B. Now what I'm going to do is list the variables that are input here. We have VI, we have friction factor, we have G, the acceleration due to gravity, And then we will calculate actually the distance to stop, xf. We need the acceleration as we saw earlier in this video. And then we're going to calculate the time that it takes to skid to that stop. Now, to do this, what I'd like to do actually is put my units in here. So our velocity, our initial velocity, we'll put in miles per hour. That's how it's given. The friction factor or the drag factor has no units, so we don't need to put anything there. Feet per second squared here. Our distance that we skid is in feet. Oh, sorry. Feet. Then our acceleration will be in feet per second squared. Same as acceleration due to gravity. And the time will be in seconds. Okay, now one thing that I like to do, I'm going to be putting formulas in here, is there's a feature that many people do not know about in Excel where you can actually name cells. So for instance, this is cell B3, but I'm going to go up here and actually name this VI. Actually, I'm not going to do that, not yet. And the reason for that is this. I'm going to have VI also in feet per second, so we'll just put it out to the side here, FPS. Okay, and this is actually the cell that I will use the value in feet per second here for VI. So I'm going to name this VI. I go here and I name this VI. This friction factor will be here, so I go here and I name this F. G, we just have to name them one by one. We'll call this XF. Oh, not in the cell, in the cell reference to it, XF. Then A, and I don't think I need to name this, but I'll name it anyway, T. Okay, now I have all my cells named. We start off with a value of 60 miles per hour here, so we'll put this here. And recall that the feet per second is actually, so I enter equals that cell times 1.467. And I know that 66 miles per hour is about 88 feet per second, and that verifies that. Our drag coefficient is 0.7. This is 32.2 feet per second squared. And now we will calculate our feet. So we need to go and look at our formula for feet. And what that is that is VI squared divided by the quantity 2 times F times G. So we go here and we put in equals VI squared divided by quantity 2 times F times G. Okay, and it says that we're skidding 171.86 blah 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 feet. We calculated 172 before, or I gave it as 172 before, and actually this number of significant digits is a little bit misleading, so I'm going to format the cells, pick number here, and then let me move this up here so it can be seen. Just change this to 0. Okay, the acceleration turned out to be minus the initial velocity squared divided by 2 times the final skidding distance. So I'll put that formula in, equals minus VI squared divided by 2 times XF. Okay, and actually I left the minus sign off, so I put the minus sign in there. Let's see, why did this not turn out to be minus? Oh, I think what's happening is that it's including the minus sign with the VI. So what I'm going to do is put some parentheses in here so that the preference is given to squaring that first. Yes, that's exactly what happened. So we're squaring that negative number, and it shouldn't have. Okay, now the time is actually, the formula that we had for that is equal to minus the initial velocity divided by A. Oh, it did not like that. So let's see what's wrong here. I think I have A. Yep, A is not listed here as, see, it does not say A here. So I'm going to go back here and hit A, and that should clear the formula up. And it says that we will slide 3.9 blah 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 91 seconds. I'll change this also. Format cells. I'll move this up so it is included in here. Number, and we'll just use 2, and there we have it. So that's how you do the calculations for that we had previously worked out in variable form and also numerically. I recommend doing them in Excel. Thanks for watching. That's the end of this video. Thank you for watching. We invite you to visit the PolyX website, where you'll find other videos on accident reconstruction and other engineering items of interest that we're interested and involved in at PolyX Engineering. Thank you for watching.